Hello, welcome to the Electronics Merit Badge. My name is Paul Chin. I'm the Scoutmaster for Troop 568. And I like to do the Electronics Merit Badge first before robotics because it allows you to build circuits and have the brains of the robot actually trigger things. So electronics is a bit broader. Almost everything you have has electronics in it. So it's exciting to get you guys introduced to something that is fundamentally used in every field that's out there. So I won't go through all the requirements. Today, I would say we will get you through number one and number two, and then you should be able to be launched into number four, where you're discussing other things and learning about other things on your own in terms of control and digital logic. And I'll give you a resource for that. A couple of resources here that will help you a lot is, of course, the merit badge pamphlet. I encourage you to either purchase or peruse for a version online and take a look. There's a lot of concepts here. If you're a reader and like can zone in and read from reading, that's excellent. Definitely go through this stuff. When we're buying parts, if you're taking my course, I've given a suggestion on what to buy to your parents. The kits are definitely readily available online and awesome to use. So basic electronics theory, I will cover that today. We'll cover what a conductor, insulator, current, voltage, and resistance, and Ohm's law as well today. So let us get started. And so after this section, I definitely want to point you to a an online presentation version of what I'm about to present from Troop 344 in Pemberton, Ohio. This deck is a more, again, not the pamphlet, but not quite the visuals that I have, but a great framework for actually understanding the same concept again. So sometimes you need to look at things a couple of times, but sometimes it can be explained to you. So let me go with it. And my goal is to really give you the terminology, kind of the 101. And again, I'm the head of global electronics, but I also run technical program management, software test, and my team spends probably 40% of the time in electronics, 60% in quote unquote programming and software. And so 30,000 foot level, electronics is like a human body. When you look at my TV remote here, the outside has an enclosure to it, and the inside has all the electronics. So most of the time, you're not looking at what we call the raw PCB. And I'm not going to make you make a PCB, but someday you'll get there. But these serve as kind of the skeleton for all the other stuff that goes on there. But but if you think of your cell phone, it has a brain, it has a processor. I think Qualcomm Snapdragon is a very famous processor that runs your cell phone. Input systems just like this. It's a touch screen, or you can have a button. So you can have a button that activates a remote. When you get to robotics, hitting this button or doing something might cause your robot to do things, roll, move, throw, using a motor. All of these robotic systems or electronic systems has some form of storage, even if it's very small amount. This one will activate the program that's in the controller that might activate the code that's stored in memory. And so it has a storage system like your brain, it has a processing system like your brain. On the output side, actually, this is really cool. This one actually will turn on my TV by emitting an IR signal. But in this case, it also is giving you a red light. So it's giving the human user of this remote an indication of what's happening. We mentioned the enclosure, so it's actually a very important part of electronics because we don't want to be touching the bare parts, the PCB. And I mentioned two-way communication. It can be RF, radio frequency. There's light version, infrared, IR, Ethernet, Wi-Fi, etc. And then finally, the circuitry and power, AC or DC, those kind of thing. We'll cover power today. So let's keep it exciting, all right? 101 electronic basics, firing electronics across the two leads. Electricity, What is it? It's a form of energy that results from a charged particle carried through a conductive material. Has a charge. This one doesn't have a charge. That charge wants to go towards what we call ground. It's going through the electricity has to go through a conductive material, and so those can come in the form of aluminum, copper, brass, anything that conducts electricity. Water is that's why they tell you when we have lightning strikes during summer camp to get out of the pool. Water is a conductor, and in fact, there's a certain level of water content in Play-Doh, so Play-Doh is a conductive material. Some are more conductive than others. Insulator material is the stuff that goes on the outside of the wire so that you don't feel the charge. It can be plastic, polyurethane, anything that does not conduct electricity. And the dielectric is an interesting form of insulator. It's something that, when placed between two conductors, creates an ability to hold a charge. And so that's actually where you start to get the concept of what a capacitor is. You have a capacitor that can hold a charge. You get a couple more of those, and you actually start to build up the concept of having a battery. So, electricity and power, we mentioned a charge item flowing down into what we call ground. I want to start with the bottom. Ground is the zero potential, so it's where that water ends up. Voltage is that potential. It's like this water tank above. If you have a gigantic, big water tank, it has a bigger voltage. So that's the way to think of it as potential. Current is the flow of those electrical charge measured in amps. And you can think of amperage or current to be the width of the pipe visually, right? Small current, small pipe, big current, big pipe. So people often think of how do I zap myself and it be dangerous. You can have a very high voltage, very high voltage, 200 volts. But if that pipe is very small, the current that's going to go through you is very small, then it's not actually that dangerous. It's the current that kills you with some voltage, if you will. Resistance is the difficulty encountered by the power source in forcing that electric current through an electrical circuit. Is measured in ohms. In reality, we can conduct electricity. We're not the best. We're not as good as wire. But if lightning strikes me and I'm over here, I am the resistance, right? I'm the one carrying the potential in the ground. It won't be a straight shot to zero. Full voltage value like 12 volts down to zero, it is going to have some resistance there. And so um, this is in the concept of direct current. There will be a different version of resistance called impedance when we talk about alternating current. So direct current systems are ones that we're most familiar with when we're doing low voltage electronics. It's one that we use when we have batteries. So your cell phone actually runs off of a DC battery. AC is, yeah, alternating current is an efficient way to transfer power over a wire. DC is actually the most efficient way, the lowest power way to actually have a circuit do something. So it was first demonstrated by Alessandro Volta in via the first battery. And so here we have a 1.5 volt battery. That's a kind of a primary AAA. And if you plot the voltage over time, it stays constant, 1.5 volts. It will drop off over time. In the center is our concept of a circuit diagram. We put a battery in one form, circuit symbol notation on the top side, where there's a resistance really representing the light there. There's a voltage and current going across that resistance, right? So very similar to this voltage through that pipe and through this pipe that has that resistance. All right, so why would we even want to do this? Well, it's actually all around trying to get something to happen. So I actually added an LED here, a symbol for a light, and a resistor down here. Here's a battery, and we're going to play with this thing called Ohm's law. Turns out if you have a DC circuit, the voltage is equal to the current times the resistance. We can think of that as voltage equals insect times rabbit because insects and rabbit are crawling around the ground. Current or insect equals voltage that fly vulture voltage flying over rabbit, and also resistance equals voltage or vulture flying over insect. Nice theory. Let's go build it up. I want to introduce you guys to a great tool. Obviously, you're going to buy an electrical kit that has a breadboard, hopefully a battery system, wires, and LEDs. But if you go to Tinkercad, they have most people are familiar with the 3D, but they actually have a circuits program. And in there, you can go and create a system. So I already created one here, but let's go from scratch. These represent real physical things that you can own and buy. And so I'm gonna go. So sorry. Let's get this out of the way. I'm gonna do things like delete everything that's in the circuit because it's a great way to teach you how to build it visually, and then when you physically do it, you're doing the same thing. All right, there's our breadboard. You will have one of these that makes things convenient. Let's go ahead and pull up a 9-volt battery. You don't have to use 9 volts, but that's what I'm using for this simulation here. All right, I'm gonna put the negative to the negative rail here. And what that does is every hole across here is going to be connected to the negative rail, or what we call ground. I'm gonna take the positive and also connect it there. And I like to make the colors true. So red is going to have the voltage, if you will, also 0 to 9 volts. And then I like to connect my rails so I can use both sides. So I'm going to connect the positive to positive, and then the negative to negative. And when you get a real breadboard, you should do the same thing using wires. All right. So we have a great convenient tool over here called an ohm meter. And so I'm going to bring one over here. And what's great about, let's see here. What's great about this is this actually represents a real ohm meter. I have one right here, where instead of physically doing it, you can use that as a digital version. But I can measure voltages here. If I put this to one end of the battery, a 9-volt battery, and put this to another, it'll show 9 volts on the screen. We're going to do a similar thing with the digital version here. And let's go ahead and play with it. Put the negative there and the positive. Let's see. I always like to keep myself color true. If I start the simulation, we should be able to read 9 volts. All right. So that's not as interesting. We know that's a battery. Let's go ahead and build out that circuit that we saw earlier. Um, so we're going to go ahead and pull out this LED. An LED has polarity. And let's go back to our definition here. Um, the LED has an anode, which is a positive end, and a cathode. The physical LED actually has a longer end, which is why it's represented by a twisted longer part, so the anode. And then the cathode, the negative end, is on a shorter run. So they tried to simulate that look by giving it a little twist there. And so let's go ahead and put this here. And so we're going to create a positive to negative immediate run. This you should not do, actually. 9 volts is not 1.5 volts, but let's go ahead and play it out. Boom. I blew up my LED. Not good, right? So with 9 volts, different than 1.5 volts. Let's see if we can change the. No, they won't change the battery type for us. So let's go ahead and get this shifted over. We're going to have to add resistance. And so let's go ahead and get a resistor here. And I'm going to rotate it around. One more. Then I'm going to stick it into the hole where the cathode is. And I'm going to move and move this up. So now with this resistor, let's give it a value. Okay, let's leave it at 1 kilo ohm. Now, if I run it, hopefully the resistor is taking on some of the current and reducing the amount of current through the LED. And so that is there. That's actually what's happening. All right. So what some fun things to try out here is, well, what is actually um, what is the value of the current that's going through that resistor? So the first thing we may want to do is measure the voltage. Measure the voltage, leave that black, that's going from the cathode across this resistor in the ground. And so let's go ahead and put this to ground here and measure the voltage there. I always like to keep it red. Obviously, it's counterintuitive, but the cathode or the negative end is still having some draw across that resistor. So let's start the simulation. So you can see that actually at the top of the LED, it's going to measure 9 volts, but at the bottom of the LED, it's only 7 volts. So it means it's lost 2 volts there, right? And to double check that again, we'll put it at the top. And so this is almost 9 volts at the top of the LED, and through the LED was a loss of 2 volts. Okay. And so, that's interesting. Let's do another thing. Why don't we measure, so we know the voltage drop is there. Let's measure the, so to do current, you actually have to put this meter in between the circuit. So it has to be inside that circuit itself. Let's put the current there. Simulation. Okay, so it's 7.04 milliamps. All right. So if you know it's 7.04 milliamps and it's running across that resistor, we should have gotten the same value, right? So we know this is a thousand. You know, this is 1,000 ohms, and it's times 7.04 milliamps. That would give you the voltage. And so let's go ahead and do the math here, right? So the resistance is kilo ohm, so it's 1,000, and then we measured the current to be 0.00704. And so voila, the voltage equals the current times the resistance. All right. A good question though was, hey, what is the resistance across that LED? That's probably a bigger question. We have 7.04 milliamps, and that's still going through that LED. Um, Man, we definitely want to figure out what that resistance is. It should be, in theory, according to our calculations, we have a loss of 2 volts divided by 7.04. So let's go ahead and do that. Minus 9, be a negative number. Okay, minus 1.96. A voltage was lost across that LED or light emitting diode. Let's divide by 0.00704, which is the current. And so we should get measure some value of 278 ohms theoretically. All right. So when you're measuring resistance, you can't do it on a live circuit. So we're gonna do things like disconnect the ground there, and disconnect the power there for now, and let's just go ahead and put up. So whenever you're doing a resistance measurement, you don't want any power going through anything. Okay, and then let's put on the resistance thing. So the reason it's not measuring anything is this is called a diode. And so we're going to have to trust that we actually have a resistance value going across there. Um, here's another way to test out our resistance measurement. Let's go ahead and put this one. I might have to reverse the values there. Oh, okay. So now I'm going to measure the resistance. And so you can see I can measure resistance across there, but across a diode, it's difficult because the diode draws current. It's a different function, but we can trust that in circuit, that's actually about 278 internal resistance once everything's put together. All right, so that's a run through Tinkercad. Let's get back to our presentation and take a look at we got through Ohm's law, alternating current. This one is a type of power that uses electrical current that periodically reverses direction. It was first built by Hippolyte Pixies, but supported by Thomas Edison. AC has proven to be a more efficient way to transfer power over long distances. Here's a circuit diagram for just generically a AC current going across what should be an impedance. If you look at the timing diagram for the voltage, it looks like a sine wave. It goes up to 1 and down to -1 and back to 0 and sends a wave quick of power down. Yeah, negative voltage is it's relative to a zero value. Right, so when we think of voltage and peaks and waveforms, there's a frequency to it. I won't go through this in detail. It's complicated. But if we think of waveforms in general, like RF, radio frequency waveforms and all that, we're using the same principles of energy being transferred. And yeah, so just really to back it up so that scouts can have fun with this. AC, you can think of it as a giver. It consumes. It's used by electric motors, or it's a way to transfer electricity. Typical voltages are, maybe shocking to you, if you will, all pun intended. 120 volts AC in the UK, 240 volts. The frequency is 60 hertz, 50 hertz in the UK. And current is typically measured in the milliamps, amps, and kiloamps, depending on what you're trying to do. With DC, it's almost everything else. It consumes electricity for the most common form in electronic boards. Transfer, it's too long of an explanation, but DC, direct current, isn't a great way to transfer electricity. Thomas Edison fought Tesla over this, and Nikola Tesla won. Typical voltage, 1.8 volts, 2, 3. So it's low voltage. You can go all the way up to 36 volts. Your car runs at 12 volts. There's no frequency. It's a direct current, so it means direct source voltage, so it's constant. Typical currents are in the milliamps. All right. And so I think this gets you started into electronics. Here's my joke. Please stay still. I want to charge my phone. If you own a cell phone, if you do anything out there, you might not realize it, but electricity and electronics has been a part of your life. And with that, this is the end of session 1. We'll cover some more concepts in session 2.